you very much. I would like to invite to the stage to another professional in the semiconductor industry. He is the head of the Digital System Integrated Circuit Division at CEA, Dombek. Welcome.
Hello, good morning, everybody. So it's my pleasure to share some words in this exciting event today. Over the years, RISC-V indeed comes to the heart of our activities, and so it was our honor to co-organize this event this year in Paris. So this morning I will quickly give a short overview of the design activities related to RISC-V, come back to our reasons to bet on RISC-V and open hardware, and show some related achievements in this area. So at CEA, the design activities range from ultra-low power circuits up to high-performance computing systems. But just for those who may not know CEA, so CEA is one of the big RTOs in Europe with 4 major domains: security and defense, fundamental research, energy, and all the technology research that is needed in all of these domains. Since our creation 80 years ago, the top topic is always sovereignty, security of the systems, and this is also reflected in our activities in the RISC-V domain. So inside the technology organization, in the microelectronics domain and digital systems, the 2 institutes, LITE and LIST, host a lot of technology platforms that range from software environments, industrial-grade tools, to industrial-grade test platforms and private white rooms. This enables to do on the research part through the path to industry, running around several hundred partnerships, and for some advanced technologies, startups that are created to bring this into the market. So for those who are interested, you could follow the link to learn more on the activities on the broad semiconductor up to system level. So in our division, the challenge is around how to create innovative software, hardware technology that is supplying high efficiency, trustworthy systems, and of course, today, this will embed more and more AI in the systems. So over the years, we were at the forefront of heterogeneous integration, photonics, always with a close link to semiconductor technology, ultra-low power systems, and efficient AI. As you see, we have used in the past a lot of different type of processing systems, but more and more the actual research goes around RISC-V processors and surrounding systems. So before coming to more detail on some of the RISC-V related products, I just want to give some words on Intact, which over 10 years ago, as soon as 3D integration technology became available, we have showcased a full system, including 96 processors, all the interconnect, 6 chiplets connected on an active interposer. So this is technology that you find today in high-performance systems, but we believe that there are still valid challenges for the open hardware community to push this and get most of the upcoming semiconductor technologies for these heterogeneous systems. So in all this big scope, why we bet on RISC-V and open hardware? This seems an obvious choice for us. Looking broadly, we're talking about how to realize the future challenges in this domain. Our vision is aligned what is described in the European High-Speed Roadmap as large, fully interconnected, distributed systems that will have to interact seamlessly between all the components, still guaranteeing performance and security of all the applications. To realize this in an even faster pace of innovation, you're meeting a lot of challenges, especially if we look at the huge design space that we are looking at, going from ultra-low power up to high-performance systems, and having the challenge to bring faster innovation to industrial benefit. So at CEA, our first concern, of course, is sovereignty, security of the systems. But then this has, of course, to go along with a lot of other challenges to maintain efficiency, scalability of these solutions, and all the other aspects that you will have to respect in such a system. To do so, we have to build on independent code that is auditable, guarantees interoperability with different elements, and still allows deep optimization, system technology co-optimization in the heart of the architecture. So all these different requirements points to support that will be open hardware, and in particular RISC-V. Indeed, RISC-V being open code, hosted by an open general foundation, as a flexible standard that allows to do deep optimization inside the system. It was said earlier how to specialize architectures to the workload today. Building on a large ecosystem with shared developments seems for us the key to build to reach all these challenges. So if I come now to some of the examples that try to illustrate the large range of activities that are going on at CEA around RISC-V, I take the same challenges, and I will not go too much into detail, of course, in systems where we use RISC-V as a controller, for instance, around new memory systems. It is used as orchestrating and interfacing for AI application, which is a topic on its own. But along all these developments, CEA is contributing to some IPs, core building blocks, also verification, which is a very important topic around, of course, every hardware development, and direct contributions to some of the open hardware cores. I will give a bit more detail on the three examples on top. Security-based systems in the high-performance space around how to change some accelerators, and in particular, first example, the high-performance D-cache, which is the major contribution to the open hardware foundation, a key element, of course, in performance of a processor. So starting with this, the HPD cache delivers high throughput, low latency solution, being compatible with a very flexible, irregular workload. So technically, from several requesters going into an out-of-order execution with a pipeline architecture, this means that you can have a huge number of outstanding requests without losing performance on individual cores and coprocessors. So today, this around 3 times performance gain and flexibility brings this cache to being standard to the CEA-6 processor, and being used in some future upcoming projects in automotive and defense space. So this cache is distributed along with a full industrial-grade verification environment, which, as I said, is key, and allows a flexible variety of applications. So it has, of course, already been integrated in 32 and 64-bit processor configurations. As you see in some of the benchmarks, you have a gain depending on the type and the irregularity of the workload compared to classical cache solutions, and this all with a negligible area overhead. Combining two of our topics, this was also key in realization I will come to for our extended variable precision coprocessor, which is deeply integrated in RISC-V core and gives the typical configuration where irregular, sometimes large data with bandwidth, data with access to memory has to be handled in a very efficient way to achieve performance in this type of particular architecture. So coming to this was what the reason to build such an architecture, where the tendency today is rather going to low precision, very parallel computation for AI workloads, but still in the space of high performance computing and numerical simulations, optimizations, precision is sometimes a key to be efficient, and software emulation of large words of floating point operation is simply too slow. So the goal with its architecture was to build a processor that will only be memory limited like all the other processing elements, but will be able to execute high complexity operations inside the processor. So this meant that we had to completely review register architecture and width, how to access this, out-of-order execution of these type of instructions, of course with this benefit to a close link to the APD cache, and in the end serving 7 functional units that natively work on 64 or 128-bit chunks of data, realizing a full compatible up to 512-bit floating point operation. Having integrated this deeply in the processor and linked to the cache by prefetching, you can keep low the penalty in bandwidth and latency of the system. And this full system has already been implemented on silicon in the framework of the API, European Processor Initiative project, and some additional work throughout this Tristan European project. So last but not least, I come back to security. In this area, our approach is to have a test vehicle, a platform that is designed to integrate both core modifications, security features inside the RISC-V processor, and key IP like crypto, of course, but also peripherals with some security features in a silicon platform that enables to test and qualify these. So there are already 4 generations of this platform that incrementally integrated more and more features that can be qualified on silicon against software and hardware attacks. For the future, this platform seems for us also to be a good basis for collaboration, since you could integrate IP to create a dedicated security product, or new ideas, concepts, and IPs to be qualified on silicon in this already mastered environment. So if you're interested, don't hesitate to visit my colleagues on the booth to discuss around the system. So to conclude with some perspectives, as you have seen, CEA is really committed to support the fast innovation and sovereign approach that is going on around open hardware in the European ecosystem. This is the reason that we are, of course, member in RISC-V and active contributor in the Open Hardware Foundation. I mentioned not all, just 2 European projects, just to stress that it's not all about hardware. Important aspects are also the modeling tool aspect around all these architectures that are also key to the efficiency of the global solutions that will be built in the future around this. So as perspectives, our future work will focus about heterogeneous systems. It was stressed earlier, we need new standards, not only on the processor itself, but on the whole system, how to build efficient systems, heterogeneous integration based on chiplets, and efficient interconnect to memory. Of course, security will remain one of our main topics, how to protect systems against ever-evolving threats. And HPC and the new next compute paradigm will bring us a lot of new challenges that we do explore. And as a small example, we already started with our partner INRIA work about RISC-V 108-bit architecture, exploring what was bringing as implications and challenges in the future. So already thank you for your time, and of course I invite you to meet me and my colleagues around our booth or the various talks and posters that we are showing in the coming days. Thank you.